So in this video, I want to show an example of making our own type class and use that to play around more with the idea of type classes and how they work. So the type class that I want to make so we're going to define a type class called Listable, and this says a type A is listable if there is a function called toList, which can turn an A into a list of integers. Okay, so let's make a couple instances of this. So I can say instance listable. Let's make an instance for integer. So this says, okay, in order for integer to be an instance of listable, I need to implement a function called toList, which has type integer to list of integer. So toList, I can actually put that type in a comment. So toList is supposed to have type, because in this case A is integer, so it'll be that. And what should it do? Well, if I have an integer, x, I need to return a list of integers. Let's just return the singleton list containing x. Incidentally, you can actually put a type signature here, but I think it needs a special, it needs an instance. It needs this language extension called instance sigs, but we'll enable that because it's actually nice documentation to be able to put the type on there. Let's make one more instance. So I'll say char is listable, toList C. So C is now a char. Let me give a type signature. We're going to make a list. We need to make a list of integers. So we'll do the integer if we do there's a standard function called ord that turns a character into its ASCII code. That will return an int, so we need to call from integral to turn that into an integer. And I think it's complaining that it's not imported, so we need to import data.char, which is where we get ord from. Okay. So let's just try this out to be sure that this works. So I could say toList of x. I get the singleton list containing 120, and I say toList of 5 integer, and I get list 5. And if I ask for the type of toList, it says, oh, toList will take an A and return a list of integer as long as A is some type that's an instance of listable. And one thing I want to emphasize here is that what actually happens when we evaluate these two expressions here. So toList of character x and toList of 5 integer. So essentially what happens is that Haskell is doing type inference, and it figures out, okay, the type of this x is char, and so we're calling toList on an argument of type char, and that is only okay if char is an instance of listable. So it goes over here and finds this instance of listable for char, and it says, aha, this is the specific implementation of toList that I need to use. So when we call toList here, it is actually picking this implementation of toList to run. And here, of course, we told it that 5 is an integer, and so it picks this instance and it calls this version of toList. So every time we call toList, it's actually choosing something to do based on the type of the input. And that's kind of exactly what we said that you can't do just with a plain polymorphic function. So this basically is giving us the ability to decide what to do based on the type of something, but it's doing it in a very principled way. And in fact, it's still not doing, it's actually doing it all at compile time. So basically, when it compiles this, it says, oh, I can figure out that this argument is an integer, so therefore I'm going to replace this toList with a specific version of toList that does this. It's not doing it at runtime and deciding what type the argument is and choosing what to do there. It figures out everything when it's compiling it and type checking it, and it replaces each call to toList with a specific version that makes sense at that place. Essentially, I'm sweeping a little bit under the rug, but okay. Let's make a few more instances now. So we could let's make an instance for our type Q. So we made this data type Q up here in the previous video. I need to implement toList, which is going to be of type Q to list of integer. And Q, let's see, a Q, we need a pattern match on the Q. It could be an A, B, or a C. And the C will contain a, whoops, there we go. There we go, that's better. So if it's an A, we could return, I don't know, any list of integers we want, 3, 44, 7. And toList B, I want that to be the empty list. And toList C, well, C contains a char. I'm just going to call toList on that C. So here's another important thing to point out, right? If you just look at this, if you don't think about the context, you look at this, this looks recursive. Right? It looks like we're recursively calling toList on this C. It's not really recursive, right? Because this toList over here is the toList for char. So this version of toList is calling this version of toList up here. And of course Haskell figures that out because it knows that the C constructor of the Q data type contains a char, and so it knows that C is char, and so it knows to pick the right version of toList. Let's do that. And so we could test this out, and if we say, toList of A is that, toList of B is that, and toList of C containing an X is the same as toList of the char X. What else can we do? Here's something fun we can do. Let's see if what if we can make an instance of Listable for pairs. So if I have a pair of an A and a B, so I'm not going to put the type signature this time. So we're going to take a pair of an X and a Y, and what I want to do, I want to turn X into a list of integers and Y into a list of integers, and then just concatenate the results. So I'm going to say something like toList X plus toList Y. Okay, but this is going to be an error. And why? It says, down here at the bottom, it says no instance for listable A arising from a use of toList. So it's you use toList on this X, which has type A, but I don't know, I have no guarantee that there's going to be an instance of listable for A. And actually, the possible fix that it tells us here is good. It says possibly you could fix it by adding listable A to the context of the instance declaration. So that's what it's talking about. Is here we could say we can do this. Okay, so similarly to this is a very similar usage of the double arrow as in a type signature that we've seen. So this says list of a pair of AB can be an instance of listable as long as the type A is itself an instance of listable. And actually, of course, I need B to also be an instance of listable. And the way I combine multiple of these is I put them, I separate them with a comma, put them in parentheses. So this says as long as A and B are both listable, then the pair, a pair type AB can also be listable. We could also make an instance and say as long as A is listable, then a list of A is listable. We can right, so we're given a list of A's, and we have to return a list of integers. And the fact that the type A itself is listable means each individual A in the list I could turn into a list of integers. So I want to say map toList X's. So I'm going to turn every single item in the list into a list of integers. That's going to give me a list of lists of integers. And then I want to call concat to turn that into one big flattened list. So for example, if I said toList of x, y, z, right? I get toList on x just gave me a singleton list of 120 y and z similarly, and I can combine those all into one thing. The fun thing is that this a here, right, the a in this type could itself be a list type. So I could do something like this: x, y, z, a, b, f, r, z, and that works just fine. So the instance, so it figured out this is a list of char, and it said, aha, that matches this one. So that's going to be listable as long as list of char is listable. And that in turn is going to be listable as long as char is listable. And it does this kind of twice. Gets us this. Okay, feel free to play around with this. Try making your own instances of listable for other types. Try changing some of the ones that we did. See if you can understand what's going on and how Haskell is picking the right implementations of toList to use depending on what type of thing you give it.